Hello students, in this video we will go over chapter 4, binomial distributions, the probability of certain binomials. So a binomial, as it says, is a series of attempts or trials or things happening in which there are only two outcomes possible on any single trial. So we can determine the probability of certain events occurring. Some of the characteristics is that each trial is identical. Each trial has only two possible outcomes. The probabilities of those outcomes don't change as we go from one trial to the next trial, and the trials are independent of each other. Some examples that we can discuss and that will help us understand binomials and what we mean here is we can have things that are independent. We talked about coins. Coins are good examples. So each trial is identical. Each coin is identical. A toss of the coin, I should say, is identical. Each trial has two possible outcomes, heads or tails. In statistics within this chapter, we basically just refer to as success or failure. So success being heads, failure being tails, or vice versa. The probability of success and the probability of failure are the same for each trial. So 50% chance to toss a coin and get heads, 50% chance of tossing the second coin or the next coin and getting heads is the same, so it hasn't changed, and the trials are independent of each other. So that is a good example of binomial distribution. However, how about dice? A six-sided dice, or six-sided die, if you wish. We roll that die, and we keep rolling that die, so it's the same six-sided die that we are rolling. So each trial, each toss, or roll of that die would be identical. Does each trial or each roll have two possible outcomes? We have a six-sided dice or six-sided die, so we think, well, no, there's six outcomes. But it all depends how we define success and failure. Perhaps success is looking for rolling and trying to get a 3. So a failure is basically not 3. It'll be a 1, 2, 4, 5, or 6. So in this case, yes, rolling a die would be good for that second characteristic. The probability of success, probability of failure are the same for each trial. We're rolling a die. So we roll one die, the probability of getting a 3 is still 1 out of 6. Rolling the die again, the probability of rolling a 3 is still 1 out of 6. And the trials are independent of each other. We're not, the second dice roll does not affect the third dice roll, for example. So dice works in this case. Let's talk about maybe cards, because these are things that are going to be always independent. So cards with replacement. We pick one card, we put it back in. So there's always 52 cards. So we are trying to pick maybe an ace. So each time we pick a card, the trials are identical. Each trial does have two possible outcomes. We're looking for an ace would be success, and basically a failure would be anything except for that ace, so not an ace. The probability does not change if we put the cards back, and the trials are independent of each other. So those are some good examples. We can also talk about perhaps a multiple choice question test. Say there's 10 questions with 4 options per question, so A, B, C, or D. So there's those 4 options, and as long as we still have 4 options, each trial is identical. Each trial has two possible outcomes, either correct or wrong for that multiple choice test. Sure, there's a greater chance of getting a question wrong, but still there are two possible outcomes. And they are the same for each trial, and the trials are independent of each other. Just because you got the first question right doesn't mean that you have a greater chance of getting the second question right. There's still 4 outcomes, which means the probability is 1 out of 4. So those are good examples. We can also bring in other examples that we'll talk about throughout this course, throughout this chapter. The binomial distribution formula is this. So if we look at this formula, what we're going to do is we're going to divide it into 3 parts. Let's get my red. So we have NCX, this is one part. Basically everything up to this point here. I can't draw straight going up and down. NCX. That's one part. This is the same as it says here as NCR. So you have that NCR function on your calculator, or we have that formula NCR. We just use X for binomials. So that's part 1. That's one calculation we need to do. The second calculation is this middle part, right in here. P to the power X. P is the probability of success on any one trial. If we're talking about coins, the probability of success is 0.5. If we're talking about rolling a die, the probability of getting a 3, for example, is 1 out of 6. If we're talking about a quiz, multiple choice part of a quiz, when you have 4 options per question, the probability would be 0.25. And to the power X. X is basically how many successes we are looking for in a question. The third part we have to calculate is this one that looks a little longer. It's basically 1 minus P. So if P is 0.25, 1 minus P is going to be 0.75, and to the power N minus X. So if we're looking for X equals 4, and say N is 6, then of course N minus X would be 2. In some books, if you're using other books, they state that 1 minus P is just Q. So just something to be aware of. So let's look over this example here. A multiple choice test consists of 5 questions. With four options, A, B, C, or D per question. And we want to know what's the probability of getting 4 correct, exactly 4. So getting 80% on this test. The first thing we need to do is determine the values for N, P, and X. So N is the total number of trials or coin tosses or dice rolls or questions we have. So N equals 5. X is always part of the question. What's the probability of getting a certain number of things correct or right or successes? So X equals 4. P is the probability of success in any one trial, or in this case, any one question. Well, we know that there are 4 options per question. Only one of those options would be correct, so the probability is 1 out of 4, or we can simplify that to a decimal as 0.25. So that's the values for N, P, and X. Now in this next slide, we will look at the calculating the probability of getting 4 correct, and then the probability of getting at least 1 correct. So let's look at that first probability of 4 correct. So let's write down the values we have. N equals 5, P equals 0.25, and X equals 4. So the formula, we want to know the probability that X equals exactly 4. It equals 5CX, or 5C4, I should say, 5C4. Let's make that a nice 4. You know what, I am a little perfectionist sometimes. So, there we have it, 5C4. Then the second part is P to the power X. I'm going to give some space here, but basically we are multiplying these 3 things. 0.25 to the power 4, and then it's going to be 1 minus 0.25. So I'm going to write in 0.75 to the power x minus, or n minus x. N minus x is 1. So there's 3 parts here, and we are going to multiply those 3 numbers out. 5c4, we can do that the long way, 5 factorial divided by 4 factorial, or we can just use the function on our calculator. We'll get a value of 5. The middle part, 0.25 to the power 4, it's always a good idea to go to at least 4 decimal places here. And 0.75 to the power 1 is just 0.75. So this answer, the probability of getting exactly 4 is 0.0146. So slightly less than, we can change that to percentage if we want, slightly less than 1.5%. We got exactly 1.46%. Okay, so let's go back to the other question we have. Probability of getting at least 1 correct. So keep in mind here, at least 1. What does at least 1 mean? At least 1 means x equals 1, 2, 3, 4, or 5. Not 0. So I'm going to show you the short way to do this, because in essence this question where it says at least 1 means we have to do the calculation for 1, 2, 3, 4, and 5. So there's going to be 5 different calculations, and then we would add them up. We know that a binomial distribution works with whole numbers. X, the values for x have to be whole numbers. The only thing that's missing is 0. If we were to calculate the probability for 0, 1, 2, 3, 4, and 5, add them up, we would get a value of 1. So not 0 basically is everything. Except 0. That's what at least 1 means. And that's how we're going to use it to solve, help us solve this next question here. So we still know that n equals 5, p equals 0.25, and x equals, we want at least 1. So we're going to solve when x equals 0. So the probability of x being at least 1 is going to equal 1 minus the probability when x equals 0. Everything right there except for 0. So 1 minus 5c0 times 0.25 to the power 0 times 1 minus 0.25, or 0.75 to the power 5. 1 minus 5c0 is 1. 0.25 to the power 0 is also 1. Basically, any number to the power 0 is 1. 0.75 to the power 5. Let's use my notes here. 0.75 to the power 5 is 0.2373. So this would be 1 minus 0.2373. This equals 0.7627. So the probability of getting at least 1 correct answer, doesn't matter which one, just one of those 5, is 76.27%. And it's preferred to keep your answer to 4 decimal places. You don't have to change it to percent. You can just list it here.